So when we last left off, we focused on drawing reasonable reaction mechanisms. So we discussed some elimination reactions. So we have an elimination reaction that we're looking at today, and I'd like someone using the annotate feature to volunteer and attempt to draw a mechanism for the following 1,2 elimination reaction. So let's take about 3 to 4 minutes to work on drawing the mechanism for that 1,2 elimination. And key thing, note which bonds are broken, which bonds are formed, and I'd like to have at least 1 to 2 students volunteer their input, and definitely everyone should be attempting to draw this mechanism along on their own piece of paper. And don't be shy to hit the annotate feature and give your attempt. And just remember, for 2 electrons, you draw a double-headed arrow. But otherwise, the first arrow looks good. And now are there any bonds that are breaking in this process? Yep, exactly right. Just remember to make that a double-headed arrow, but that's perfect. Exactly correct. So just to reiterate, so in 1,2 elimination, our oxygen or nitrogen atom kicks its electron down, and then the electron density in our sigma bond ends up distributed onto our leaving group. So that in turn gives us our reformed ketone or imine and an equivalent of cyanide. Perfect. Okay, let's look at another example. This time we're looking at the elimination of water. So let's take a moment. This is another 1,2 elimination. Would someone like to propose a mechanism for this elimination of water? And don't be shy to break out the annotate feature. So let's spend about 2 to 3 minutes on this mechanism. And don't be shy, it doesn't just have to be one person. Anyone can volunteer and annotate. But you should definitely be trying to draw this mechanism on your own note sheet. Just so that way when we discuss, we can correct and potentially notice any errors. So would someone like to propose a mechanism for this elimination reaction? Yep, perfect. Yep, exactly right, spot on. This is a classic 1,2 elimination reaction. Oops. So let's just redraw that mechanism so that way everyone can There we go, perfect. So we kick down our electrons to form our pi bonds, and the electrons in our sigma bonds gets kicked up to our leaving group. Exactly right. Okay, let's practice drawing a few other elimination reactions. So let's look at the dehydration and elimination of water via an E1 process. So I want you to think, when you see E1, carbocation. So would someone like to volunteer using the annotate feature? And I'm asking you to assume that the base is the following compound in this case. So don't be shy to volunteer. And notice how I have a blank space for you to draw an intermediate. So this reaction does have an intermediate. And just recall our discussion of the E1 pathway. It typically goes through a carbocation intermediate. So let's take about 2 to 3 minutes. And if someone would like to volunteer to draw a mechanism using the annotate feature, I'd be happy to discuss that. Or if you have any questions, don't be shy to message me via the chat. No. The base is part of step. So if this would be step 1, the base is part of step 2. It's not part of the intermediate. It's just what's going to be used to pull off the proton. Mm-hmm. Yep. That's exactly right. Though the process you're describing would be an E2 process. So in E1, we form our carbocation first. Would someone like to try with the annotate feature to draw a mechanism so we can discuss? If not, we'll discuss in about a minute and a half. So that process would be correct. That general arrow pushing scheme would be correct for an E2 process where the elimination occurs simultaneously. But that's very, very close. It's on the right track in terms of arrow pushing. For an E1, we make a carbocation first. So let's try to draw a carbocation intermediate. So to help everyone along and to provide a little bit of guidance on this problem, don't worry, we're just getting used to drawing mechanisms. So the first step is we form our carbocation by losing our leaving group. And then our base pulls off our proton. So we draw our arrow from our basic lone pair to our hydrogen, and then our electrons in our bond to hydrogen gets kicked down to form our alkene. Yeah, but it was very, very, very close. Perfect. So we're just getting used to the general patterns of arrow pushing. So we have our leaving group leaving in a heterolytic fashion, and then we have elimination to form an alkene from a carbocation. Perfect. So we're just practicing all these different reaction mechanisms, getting used to drawing arrow pushing mechanisms. Let's try a few more. Let's try a few more problems. So let's look at the elimination of iodide. So we'll make iodide as one of our products. And let's look at this elimination via an E2 process. So this is concerted. So the deprotonation and elimination occurs at the same time. So if someone would want to volunteer using the annotate feature, let's take about 2 to 3 minutes to draw this mechanism, and then we'll discuss. And I guess as another product, we'd also make tert-butyl alcohol as well. That's another hint for this mechanism. And don't be shy to break out the annotate feature. If not, we'll discuss in a few minutes. Yep, that description is correct, but I'd like to see someone try to draw with arrow pushing, just so that way we can look and identify some common things that are great and things that can be improved in arrow pushing. No problem. Well, to go off of Mitchell's point, so he's saying that the tert butoxide attacks hydrogen. The lone pair moves, so it's, I guess you can, rather than the lone pair, it's the bonding electrons move to form our alkene, and iodine leaves. Yep, that's exactly right. So the key feature of an E2 is that it's a concerted elimination. Okay, perfect. Okay, so let's now talk about substitution reactions. So substitution reactions involve displacement of a leaving group with a nucleophile. So the SN1, which is a classic, concerted means that the leaving group leaves at the same time that the hydrogen eliminates. So it occurs at the same time. Does that make sense? Perfect. Okay, so in an SN1 reaction, we have loss of our leaving group followed by the attack of the nucleophile on our carbocation. So an SN1 is a stepwise process. So we lose our leaving group and then our nucleophile attacks our carbocation. In an SN2 reaction, we have concerted attack of the nucleophile and loss of the leaving group. Do you notice how the attack and loss occurs in the same step for the SN2? Do Do you notice how the attack and loss occur in the same step for the SN2? Perfect. So let's draw some mechanisms here. This is a classic reaction known as the Finkelstein reaction. It's quite interesting from an equilibrium perspective, and we'll discuss it more in the chapter 9 when we discuss alkyl halides. I'd like someone to draw a mechanism for the following SN2 displacement. So don't be shy to break out the annotate tool, and we'll discuss in about 2 to 3 minutes. Okay, the first step looks good. What is that zigzag line representing? So if we notice that the Yep. So to draw that bond breaking, how about we kick those electrons in our bond onto our chlorine? Yep, there we go. And that's it. Yep, exactly right. Perfect. So let's clear and let's talk a little bit. So as your classmates alluded to, thank you, iodine attacks our carbon and the carbon-chlorine bond breaks. Perfect. Classic SN2. A concerted attack of our nucleophile and loss of our leaving group. Wonderful. So let's now do the SN1 reaction. So let's draw a mechanism for the following SN1 displacement. And if you've read the text and read the later chapter on alkyl halides, you'll also notice that this is a bit of a joke about how SN1 and SN2 reactions are classified, in that this is a genuine SN1 reaction, but it's also a unimolecular reaction. So it would look like an SN1 even if it wasn't. Would someone like to take a moment and draw a mechanism including the intermediate for the following reaction? Remember, when you think SN1, think carbocation. So notice how we have multiple distinct steps. The SN1 reaction is a stepwise reaction. So let's try to draw the mechanism for that SN1 reaction. And don't be shy to break out the annotate feature. There's enough space for 2 people to give their attempts if you're interested. I really encourage you to practice the act of just physically arrow pushing on pen and paper. I know it seems silly, but just like resonance structures, it really helps you get used to and visualize how electrons move in chemical mechanisms. Yep, intramolecular, within the same molecule. So instead of having a separate nucleophile and electrophile, they're together. Yep, the first step is perfect. Loss of our leaving group to make a carbocation. Yep, looks good so far. Yep. And now that we have our carbocation, what happens? If we need to form a bond with oxygen, what's oxygen going to do to our carbocation carbon? And you draw the next step in the second intermediate. So your pink arrow is perfect, and then you draw the second step on your intermediate. So that arrow in black was perfect. Just needs to be drawn on the intermediate. Yep, perfect. Exactly right. Wonderful. So let's discuss. I'm just going to clear and rewrite it so that way we have an instructor solution. But that was perfect. That was perfect. So first step, we lose our leaving group. Oh, let me switch to the native annotate feature in OneNote. So first step, we lose our leaving group. Okay, so step one, we lose our leaving group, and step two, our nucleophile attacks our carbocation. So this oxygen would have a positive charge. This is an example of an so intramolecular within the same molecule. Pretty cool. But if you're ever having to run kinetics and you're trying to tell the difference between an SN1 and an SN2 reaction for an intramolecular reaction, you're going to have a really rough time from a kinetics perspective. Anyway, that was perfect. That was perfect. Everyone's getting a lot better at drawing reaction mechanisms. The next fundamental step that we see a lot in reaction mechanisms are proton transfers. So in a proton transfer, a basic lone pair abstracts a proton from an acidic bond. The most basic lone pair is typically protonated first. Remember, you're going to need to know your pKa values to know the position of an acid-base equilibrium. Now, one thing I do want to make you aware of is many reactions utilize intermediates that may be minor species at equilibrium. So for example, H3O plus has a pKa of about -1.7, while a protonated ketone has a pKa of around -3. So we would expect this equilibrium clearly favors our reactants. However, this protonated ketone is a key intermediate in a lot of chemical reactions. So just because you generate a minor amount of a species doesn't mean it can't potentially be used for a reaction. Does that make sense? Does everyone recall these pKa values? If you need to, go back to the chapter 2 notes and look up the pKa table because those aren't going away. The reason why we have you get familiar with pKa values is so you can assess major and minor species at equilibrium. So let's look at another example for a proton transfer. So this amine has a pKa of around 35. This ketone has a pKa of around 22. So we'd expect this deprotonation to be relatively spontaneous. Well, let me rephrase. We'd expect this deprotonation to be thermodynamically favored. Okay? Okay, so proton transfers, intermolecular versus intramolecular. Now, this is just my pet peeve, and it does make a difference in certain reactions. So when drawing mechanisms, intramolecular proton transfers are only really possible when the acidic and basic substituents are close in space. Now, this may seem a little bit redundant to say, but just showing you a model of this to help drive home this point. Okay, so let's suppose we're looking at a cyclic system. Does everyone notice how the proton in white and our amine are able to be close together in space? Does everyone notice how they're close together in space? Yes. Okay, now, because this molecule can bring our basic substituent and our acidic proton close together, it's reasonable to draw an intramolecular proton transfer. However, if the substituents are geometrically separated, it's better to draw intermolecular proton transfer using solvent, reactant, or product molecules, because those are more geometrically allowed. To showcase this idea and to really drive home this point, so geometrically, am I ever able to bring this hydrogen as close to this oxygen here? Does everyone notice how geometrically in this molecule, this hydrogen is held at a distance from this oxygen? Does everyone notice how this molecule is geometrically constrained? So it would be far easier for me to draw another solvent molecule facilitating this proton transfer rather than having it occur intermolecularly, or sorry, intra. Inter, where we have another species, is more preferred, just because it's easier for that to happen. So in this case, we draw our proton transfer via an intermolecular pathway. Same end result, but mechanistically, it's more reflective of what's actually happening, you know? Also, you want to make sure the pKa values for the desired proton transfer products actually favor generation of your desired products. Okay. So we're now going to look at our carbocation rearrangement. So in some cases, an intermediate carbocation can undergo a rearrangement to yield a more stable carbocation. So in terms of carbocation stability, remember tertiary beats secondary, which beats primary, and so forth. Additionally, we know that carbocations are stabilized by adjacent carbon-carbon pi bonds via resonance. This is review. Now, why is this important? Well, mechanistically, there are some ways for carbocations to rearrange. The first of which is a hydride shift. It's a shift of H- from an adjacent atom to the carbocation. So when our hydride shifts, we've gone from a secondary carbocation to a tertiary carbocation. These carbocation rearrangements are driven by the stability of the resulting carbocation you generate. Does everyone understand why the product from this hydride shift is lower in energy? Does that make sense to everyone? Let me draw the plus a little bit neater. There we go. Okay, perfect. So let's keep going now. Rather than shifting a hydride equivalent, you can also undergo what are known as alkyl shifts, which are shifts of a methyl or another alkyl group from an adjacent atom to the carbocation. So in this case, we're shifting our methyl group and we're going from a secondary to a tertiary carbocation. Yes, tertiary because there are 1, 2, 3 carbons attached. Exactly right. Does that make sense? Perfect. And again, this alkyl shift is driven by the fact we're generating, in both cases, a more stable carbocation. Okay, let's keep going. Now, hydride and alkyl shifts can also be favored if the cation is stabilized via resonance. So in this case, this hydride shift occurs to generate an allylic carbocation, which is stabilized via resonance. Now, alkyl and hydride shifts can occur multiple times to generate a stable carbocation. For those in biology, does anyone recognize this scaffold? Does anyone recognize this scaffold? Anyone? Yes, you can consider it as H minus. The hydrogen in the hydride shift doesn't have a formal negative charge, but the hydrogen, it's behaving in a nucleophilic rather than electrophilic. Yep, exactly right. So this is a steroid skeleton, or a precursor to the complete steroid skeleton. Yep. Good. I'm always glad when I show students molecules relevant to biology majors that they're able to correctly identify that their biological relevance. Yeah, so in this case, you can see a chain of hydride shifts to generate a very stable tertiary carbocation. Wonderful. Now, I'd like you to predict if the following carbocations will rearrange and draw the products after rearrangement. So let's start off with this first species. I'll do the first one. So in this case, we can generate a benzylic carbocation after a hydride shift. So we'll shift our H minus equivalent. In general, it's easier to shift hydride versus alkyl groups. And we generate a highly stabilized tertiary carbocation. Okay, so let's take a moment now, and I'd like someone to attempt question number 2. So I'd like you to propose, will we observe a hydride shift for this second structure? And what would the product be for the hydride or alkyl shift? So hydride or an alkyl shift. And we'll resume to discuss in about 2 minutes. And don't be shy to break out the annotate feature to provide, oh, yep, there we go. Perfect. And don't be shy to break out the annotate feature to provide your proposed solution. And remember, hydride and alkyl shifts are driven by geometric constraints and overall generating the most stable carbocation. So allylic, benzylic, tertiary carbocations, carbocations that are stabilized via resonance, all of those are favorable for hydride and alkyl shifts. So would someone like to propose a product for the second species if it does rearrange, which we're supposing it may? When we shift our alkyl group over, where does our carbocation end up? So we moved our we moved our alkyl group over. So let's draw our new alkyl group. You're on the right track. You're very close. The first arrow pushing was spot on. And what happens when we move an alkyl group over? Where does our carbocation end up? Would anyone like to help out? Yep, it ends up on the tertiary carbon, exactly right. So to help everyone visualize that, and don't worry, I really appreciate everyone chiming in. And don't worry, for drawing mechanisms, it just takes a lot of practice. That first arrow pushing was spot on. So we're gonna shift our alkyl group. And the reason why we shift our alkyl group, is because it generates a highly stabilized tertiary carbocation. So as our alkyl group moves over, this carbon now has 4 substituents, and our carbocation now ends up on our allylic position. Does everyone see why this is our lowest energy potential carbocation that we can generate over, for example, the carbocation product from the hydride shift? Does everyone understand why the box product is lower in energy? Because it's tertiary allylic versus secondary. Does that make sense to everyone? Is everyone comfortable with this idea so far? Any questions on this example? Okay, let's keep going then. This is a classic intermediate in what's known as a pinnacle rearrangement. It's a classic alkyl shift, and I'd like you to draw the proposed product after the pinnacle rearrangement is completed. Again, we want to generate the most stable carbocation. So don't be shy to break out the annotate feature, and then we'll discuss in about 2 to 3 minutes. And don't be shy, don't be shy. I'm telling you, the very act of practicing an alkyl shift. So that alkyl group is already attached to our carbon. Ooh, we have something interesting. Now that's good, that's good. Keep going with that thought, or let's see where that thought goes. And just focus on trying to generate the most stable carbocation. Yes, exactly right. Yep, it would, yes. Yep, that's the key second step in the pinnacle rearrangement. So to provide everyone a little bit of guidance, so first we'll shift our alkyl group over to generate the following carbocation. Would someone like to comment as to why this carbocation is so especially stable? Why is this carbocation so stable? When we discussed carbocation stability, is there another factor that we discussed besides primary, secondary, tertiary? What's so special about the carbocation drawn? Resonance, yep, it's stabilized via resonance. You can kick our oxygen lone pair down and form the following product. So we've in effect stabilized our carbocation. Yep, so that's exactly right. So this is known as the pinnacle reaction. In case you wanted to become familiar with all the named reactions in organic chemistry, it's really good to understand them from a fundamental reaction step perspective. Any questions on this example? Oh, whoops. There we go. Sorry about that. That was a typo. Sometimes the OneNote lags out when I'm recording as well. Yep, perfect. In terms of other products, you can get some elimination. You can get some substitution products. But the pinnacle reaction is typically run in a way where the carbocation shift is favored, just because this carbon-oxygen double bond is very stable. Yeah. But you could see substitution, elimination, and other byproducts. Pinnacle reactions are sometimes quite clean, other times they just yield a mess of different products. And of course, these alkyl shifts don't have to stop. Yes, all the atoms are used. So this alkyl group here ends up on the adjacent carbon. Yep, that's exactly right. Mm-hmm. Perfect. So, we've managed to reach the end of this section. Let me pull up the supplemental for this note set. Give me one moment. Any miscellaneous questions I can address? Let me just pause recording.